Welcome to the General Chemistry 1 class. This section is on gases, focusing on the ideal gas equation. In this lesson, we will use the ideal gas equation to calculate pressure, volume, temperature, or number of moles of a gas. Let us recall the gas laws showing different relationships between pressure, volume, temperature of gases. We have Boyle's law for the pressure-volume relationship, Charles' law for volume temperature and pressure temperature relationship, and Avogadro's law for volume amount relationship. Combining equations for the gas laws gives the ideal gas equation P times divided by N times T equals a constant that is equal to R, where R is a universal gas constant. The value of R is equal to 0.0821 liter atmosphere per mole Kelvin, or 8.314 Pascal meter cube per mole Kelvin. Let us use the equation in solving problems. Let's have example number 1. Calculate the pressure exerted by 2.50 mole of argon filled in 20.0 liter vessel at 27 degrees Celsius. Here are the given with an amount of N is equal to 2.50 moles, volume is equal to 20.0 liters, and temperature is equivalent to 27 degrees Celsius or 300.15 Kelvin. What is S is the pressure exerted by the gas, or the P. The problem can be solved using the ideal gas equation, or PV is equals to nRT. Solving for P, the equation becomes P is equal to nRT divided by V. Plugging in the given values where P is 2.50 moles times 0.0821 liter atmosphere per mole Kelvin times 300.15 Kelvin divided by 20.0 liters. Canceling the units and simplifying, we get 3.08 atmospheres. Example number 2. At 350 Kelvin, 3.45 mole of fluorine gas has a pressure of 6.53 bar. What is the volume occupied by the gas? Given data are the amount in N, 3.45 moles. Pressure were 6.53 bar. Temperature is 350 Kelvin. What is S is the volume of the gas. Solution. The problem can be solved using the ideal gas equation of PV is equals to nRT. Solving for V, the equation transforms into V is equals nRT divided by P. Plugging in the given values where V is equals to 3.45 moles times 0.0821 liter atmosphere per mole Kelvin times 350 Kelvin divided by 6.53 bar. The pressure volume must be converted to atmosphere for proper cancellation of units to leave the unit L. Since 1 atmosphere is 1.01325 bar, we will multiply to 6.53 bar by the conversion factor of 1 atmosphere divided by 1.01325 bar. Canceling the units and simplifying, we get 15.4 liters. Example number 3. How many moles of helium would give a pressure of 900 millimeter of mercury in 25.0 liter vessel at 50 degrees Celsius? Given data are the pressure of P, where is equals to 900 millimeters of mercury, and V is equals to 25 liters, and temperature is 50 degrees Celsius, which is equal to 323.15 Kelvin. What is S in the problem is the amount of moles, or the N. Solution. The ideal gas equation can be used to solve the problem. From the equation PV and RT, rearranging this to solve for N. The equation becomes N is equals to PV over RT. The given pressure is in millimeters of mercury and must convert it to atmosphere, so a conversion factor will be used. So N is equals to 900 millimeters of mercury times the conversion factor of 1 atmosphere divided by 760 millimeters of mercury times 25.0 liters divided by the quantity of 0.0821 liter atmosphere per mole Kelvin times 323.15 Kelvin. Canceling the units and simplifying, we get 1.12 moles. Let's have example number 4. Calculate the temperature in degrees Celsius needed for 8.462 mole of ozone to exert 10.5 atmosphere pressure in a 25.00 liter vessel. Given a data are the amount of N where it is 8.462 moles, pressure is equals to 10.50 atmospheres and volume is equals to 25 liters. What is asked in the problem is the temperature expressed in degrees Celsius. Solution, we rearrange the ideal gas equation to solve for temperature or T. Thus, we have T is equals to PV over RT. Plugging in the values where T is 10.5 atmosphere times 25 liters divided by the quantity of 8.462 moles times 8.0821 liters atmosphere per mole Kelvin. Canceling units and simplifying, we get T, or the temperature, is equals to 337.8 Kelvin. Congratulations, and we obtained so far a temperature of value in Kelvin to convert it in degrees Celsius. Simply deduct 273.15 from 377.8, giving a temperature value equal to 104.65 degrees Celsius. Our basis for significant figures is obtained in the calculated value of 377.8 and not the correction term of 273.15. So our final answer must have one decimal place. With this, we have temperature is equals to 104.7 degrees Celsius. Let's have example number 5. Use the ideal gas equation to calculate the molar mass of a gas at standard temperature and pressure, or STP. At STP, the temperature, or T, is equals to 0 degrees Celsius, which is equal to 273.15 Kelvin, and pressure is equals to 1.00 atm. What is asked is the molar volume. Using the ideal gas equation, we can come up with the equation for solving the molar volume, or the volume divided by the number of moles, by rearranging the ideal gas equation to solve for V. Divided by N, we have V bar, or V is divided by N is equals to RT over P. Plugging in the given values, the molar volume of 0.0821 liter atmosphere per mole Kelvin times 273.15 Kelvin divided by 1 temperature, giving a value of 22.4 liters per mole. The combined gas law is a form of the ideal equation that shows the relationships between pressure, temperature, and volume of a given amount of gas. Since PV over T equals N times a constant for a fixed amount of N, the combined gas law is given by P1 times V1 divided by T1 equals P2 times V2 divided by T2. The combined gas law is a combination of Boyle's law and Charles' law. Looking at the combined gas law equation, if the temperature is constant, T1 and T2 can be cancelled since they are equal. arriving at the equation of Boyle's law. On the other hand, if the pressure is constant, cancelling the P1 and P2 leads to the equation of Charles' law for the volume-temperature relationship. If the volume is the one kept constant, cancelling the V1 and V2 results in the equation for Charles' law for pressure-temperature relationship. So let's have the example number 6. A balloon containing 0.05 mole of nitrogen gas has a volume of 1.22 liters at 298.15 Kelvin and 1.00 atmosphere. It was heated in a vacuum oven to reduce its pressure to 0.452 atmosphere at 316.15 Kelvin. What was the resulting volume of the gas? Given, we have the initial volume. V1 is 1.22 liters, the initial pressure where P1 is 1 atmosphere, the final pressure or the P2 is 0.452 atmosphere, and the initial temperature is T1 is 298.15 Kelvin. The final temperature or the T2 is 316.15 Kelvin. What is asked is the final volume. Solution. We can solve problem using the combined gas law, where P1 times V1 divided by T1 equals P2 times V2 divided by T2. Solving for V2, the equation becomes V2 is equals to P1 V1 T2 divided by P2 and T1. Plugging in the given values, we have V2 is equals to 1 atmosphere times 1.22 liters times 316.15 Kelvin divided by the quantity of 0.452 atmosphere times 298.15 Kelvin. Cancelling the units and simplifying it, we can get V2 is equals to 2.86 liters. Example number 7. In a 12-liter vessel, 1.00 mole of carbon dioxide has a pressure of 2.05 atmosphere at 300 Kelvin, at which temperature will the same amount of the gas exerted a pressure of 5.95 atmosphere in a 500-liter vessel. Given data, our initial volume of V1 is equals to 12 liters, final volume of 5 liters, initial pressure of P1 is 2.05 atmosphere, final pressure of P2 is equals to 5.95 atmospheres, and T1 is 300 Kelvin. What is asked is the final temperature or T2. Solution. Rearranging the combined gas law to solve for T2, we have T2 is equals to P2, V2, and T1 divided by P1 and V1. Plugging in the given values, we have 5.95 atmosphere times 5.00 liters times 300 Kelvin divided by the quantity of 2.05 atmospheres times 12 liters. Cancelling the units and simplifying, we obtain T2 is equals to 363 Kelvin. Another property of gases can be calculated using the ideal gas law is their density. To do this, we need to express the ideal gas equation in another form, in which mass is included in the equation. To do this, let us recall the definition of molar mass, which is the mass divided by the number of the moles of a substance. Solving for N, we have N is equals to mass divided by the molar mass. Substituting the value of N to the ideal gas equation, we have PV equals M divided by the molar mass times RT. Considering the density that the mass divided by the volume, we can write the ideal gas equation in a form that is equal to the density of a gas. simply rearrange the first equation on the screen and solve for the mass divided by the volume. From here, we can get the density equals P times molar mass divided by RT. Let's have example number 8. Calculate the density of oxygen at 25 degrees Celsius and 1.0 atmosphere. Given the data of P, or pressure 1 atmosphere, and T, 25 degrees Celsius or 298.15 Kelvin, we will calculate the density. The density of a gas is given by ρ, or P, times molar mass divided by RT. The molar mass of diatomic oxygen is 2 times 16 grams per mole, which is equal to 32 grams per mole. Substituting this and the given values to the equation for density, ρ 1.0 atm times 32.00 grams per mole divided by the quantity of 0.0821 liter atmosphere per mole Kelvin times 298.15 Kelvin, giving the answer of ρ equals 1.3 grams per liter. The ρ, it only represents the density. Ideal gas equation is the equation for calculating the molar mass of a known gas, giving its conditions. By rearranging this form of the ideal gas equation, PV is equals to mass over the molar mass times RT. The molar mass of a gas can be expressed as molar mass equals to mRT over PV. Let's have example number 9. A 0.369 gram gas sample is trapped in a 0.200 liter container, giving the pressure of 756 millimeters of mercury at 29 degrees Celsius. Determine the molar mass of the mass. Given data are mass 0.369 grams, volume which is 0.200 liters, and pressure 756 millimeters of mercury, and temperature 29 degrees Celsius or 302.15 Kelvin. What is asked is the molar mass of the gas. Solution. The molar mass can be determined using the equation of molar mass is equals to mRT over PV. Substituting the given values, we have molar mass equals to 0.369 grams multiplied by 0.0821 liter atmosphere per mole Kelvin times 302.15 Kelvin all over the quantity of 756 millimeters of mercury times the conversion factor of 1 atmosphere per 760 millimeters of mercury times 0.200 liters. Cancelling the units and simplifying, we obtained a value of 46.0 grams per mole. To summarize, ideal gas law is an equation that shows the dependence of pressure, volume, temperature, and amount of substance in moles to each other. Ideal gas equation can also be used to determine the other quantities of gas such as molar volume, density, and molar mass. We have here our references for further readings. Thank you and congratulations.